Hello friends, welcome to my lecture on cross ratios of a bilinear transformation. Now suppose first we will discuss fixed points of a transformation. So let us say suppose we have a mapping W equal to Fz, then by a fixed point of W equal to Fz we mean a point whose image under the function W equal to Fz is the same complex number, that is the fixed points of W equal to Fz are obtained from the equation Fz equal to Z. Hence, in particular the fixed points of the bilinear transformation W equal to Az plus B over Cz plus D are given by Az plus B over Cz plus D equal to Z. Okay. This can be written as Cz square minus A minus D into Z minus B equal to 0. Now, this is a quadratic equation in Z. You can see this is a quadratic equation in Z whose coefficients all vanish if and only if the mapping is the identity. You can see if the coefficients all are zeros, C equal to 0, A minus D equal to 0 and B equal to 0. Okay. Then C equal to 0, B equal to 0 and A equal to D gives you W equal to Az plus B divided by Cz plus D. So, B equal to 0, this means this is equal to 0, C equal to 0 means this is equal to 0, then A equal to D. So, it is equal to Z. So, when C is 0, B is 0, A equal to D, we get W equal to Z, that is the identity transformation. So, the coefficients all vanish, the quadratic equations coefficients all vanish if and only if the mapping is the identity. In this case A equal to D not equal to 0, B equal to C equal to 0, because we want AD minus BC to be non-zero. So, we have to take A equal to D not equal to 0. Now, therefore, we have the following result: a linear fractional transformation not the identity has at most two fixed points. Okay. If you do not want this fractional transformation to be an identity, then it will have at most two fixed points. Okay. If it has more than two fixed points, that is 3 fixed points or more fixed points, then it must be the identity transformation. Okay. So, if S and T are two bilinear transformations, we in particular as a corollary we have, if S and T are two bilinear transformations which agree at 3 distinct points of the extended complex plane, then S must be same as T. Okay. So, we can easily prove this. Suppose let us say Szj equal to Tzj, okay, for j equal to 1, 2, 3. Okay. There let us say let us take 3 distinct points Z1, Z2, Z3 in the extended complex Z plane, and suppose that S and T agree on these 3 points Z1, Z2, Z3, then S inverse let us say this composition mapping S inverse OT, because when S is a bilinear transformation, then S inverse is also bilinear transformation, and composition of two bilinear transformations is also bilinear transformation. So, S inverse OT is a bilinear transformation, and this will be equal to S inverse Tzj. So, this is equal to Tzj equal to Szj. So, S inverse Szj. S inverse Szj is equal to Zj, and this is also equal to similarly T inverse OS. In a similar manner we can say that T inverse OS at Zj equal to Zj, because this is T inverse Szj, Szj equal to Tzj and T inverse Tzj equal to Zj. So, we see that S inverse Tzj equal to T inverse OS Zj. Okay. And now, so this is a bilinear transformation, okay, S inverse OT which maps Zj into Zj. So, this by the previous theorem S inverse OT must be identity map. Okay. So, hence S inverse OT will be identity map, and same will be true for the bilinear transformation T inverse OS. Now, we want to show that S is equal to T. Okay. So, we can see that S is equal to S O S inverse. Okay. S is equal to S O S inverse. This is identity. Okay. O T. Okay. We can write T as S O S inverse O T, because S O S inverse is identity map. Okay. So, so this is equal to this, and then S O S inverse O T, okay, is equal to S O identity map, which is equal to S. Okay. So, T can be written as S O S inverse O T, but this is equal to S O S inverse O T, and S inverse O T equal to identity map. So, S O I V is equal to I. So, thus T is equal to S. So, if two bilinear transformations agree at three distinct points of the extended complex plane, then they must be same. Okay. Now, let us see an example. Find all bilinear transformations whose fixed points are minus I and I. We have seen that if W is equal to F Z, W equal to F Z equal to A Z plus B over C Z plus D, then the fixed points of this transformation are given by Z equal to A Z plus B over C Z plus D, okay, which gives you C Z square minus A minus D into Z minus B equal to 0. Okay. This equation gives us this. Okay. Now, if fixed points are I and minus I, fixed points are given by this equation. Okay. So, if I and minus I are fixed point, then let us put them here. So, let us put first I. Okay. When you put I here, C I square means minus 1 minus A minus D into I minus B equal to 0. Okay. Now, let us put minus I. So, we get minus I whole square is I square. So, again minus 1 minus I we put here. So, we get plus A minus D into I minus B equal to 0. So, let us solve these two equations. Okay. Adding these two equations, what do we get? Minus 2C, when you add them, then this middle term will cancel, and we will have minus 2C minus 2B equal to 0. So, we get B equal to minus C. Okay. B equal to minus C. Now, let us put B equal to minus C in this equation. What do we get? Minus C minus A minus D into I, and B is minus C. So, plus C equal to 0. So, this cancels with this, and what do we get? A equal to D. Okay. So, the bilinear transformation W equal to A Z plus B over C Z plus D, whose fixed points are I and minus I, has to be W equal to A Z plus B. B is equal to minus C. Okay. So, A Z plus B, okay, C is minus B. So, minus B Z, and D is equal to A. So, we get A Z plus B over A minus B Z, okay, where A and B are arbitrary, but we have to remember that A D minus B C must be non-zero. Okay. So, this is the set of all linear fractional transformations whose fixed points are minus I and I. A and B are any real numbers, but A and B are related to C and D by this equation, A D minus B C non equal to 0. Okay. Now, let us come to cross ratio. In applications, we often are required to find a conformal mapping from domain D that is bounded by circles onto a domain D dash that is bounded by lines. We can accomplish this by a bilinear transformation, but for this we need a general method to construct a linear fractional transformation W equal to S Z, which maps three given distinct points Z1, Z2, Z3, because to draw a circle we need three non-collinear points in the plane. Okay. So, which maps three given distinct points Z1, Z2, Z3 on the boundary of D to the three given distinct points W1, W2, W3 on the boundary of D dash. You can see W equal to A Z plus B over Cz plus D. Okay, because of AD minus BC not equal to 0, okay, A and C cannot be both 0. Okay, so if A is not equal to 0, we can divide by A, okay, and write it as Z plus B by A. Suppose, okay, so A and C cannot be both 0, can't be 0 simultaneously. Okay, because then AD minus BC will be 0. Okay, so suppose if A is not 0, okay, A is not 0, we can write it as AD Z plus D B by A, and here, so this will be what, A Z plus B by A, and here when A is not 0, we can have C Z plus D. Okay, so we will have to write it as A is non-zero, we are taking, D can be 0. Okay, A is not 0. So if A is not 0, then C is not 0. Okay, either C is not 0. If C is 0, then D cannot be 0. Okay, so we can take then D we can divide by D and write it as A by D and then C by D into Z plus 1. Okay. So then you can see there are only 3 ratios, A by D, B by A, C by D. They can be replaced by 3 constants. So to determine a unique transformation, unique bilinear transformation, we need to have 3 distinct points. Okay. So if we have 3 distinct points, then we can determine a unique bilinear transformation which maps 3 distinct points Z1, Z2, Z3 to 3 distinct points W1, W2, W3. So we will construct a general method to which will take us from 3 distinct points Z1, Z2, Z3 in the Z plane to 3 distinct points W1, W2, W3 in the W plane. Okay. So let us it can be done by using the cross ratio, which is defined as follows. The cross ratio of the complex number, let us take Z, Z1, Z2, Z3. Okay, Z, Z1, Z2, Z3, the complex then this cross ratio of these 4 numbers is given by this complex number Z minus Z1 over Z minus Z3, Z2 minus Z3 over Z2 minus Z1. Okay, this complex this cross ratio will help us in finding the transformation which maps the 3 points Z1, Z2, Z3 into the 3 points W1, W2, W3 in the complex plane. So to include points in the extended complex plane, because we want the linear transformation, the bilinear transformation to be defined for the extended complex plane. So to include the points in the extended complex plane, we use the limiting formula. That is for example, the cross ratio of say Z let us take at infinity Z1, Z2 and Z3, it is given by limit Z tends to Z minus Z1 over Z minus Z2, Z2 minus Z3 over Z2 minus Z1. Now the limit Z tends to infinity Z minus Z1 divided by Z minus Z2 into Z2 minus Z3 over Z2 minus Z1 is equal to limit Z tends to 0, we replace Z by 1 by Z. So 1 by Z minus Z1 divided by 1 by Z minus Z2. Okay. So this is independent of Z. Okay. So we can write this like this. So this is equal to limit Z tends to 0, 1 minus Z Z1 over 1 minus Z Z2. Okay, into Z2 minus Z3 divided by Z2 minus Z1. So this is equal to Z2 minus Z3 divided by Z2 minus Z1. Okay. So this cross ratio will then reduce to Z2 minus Z3 over Z2 minus Z1. Now in our next result we show that the invariance of cross ratio under Mobius transformation. We are going to show that the cross ratio remains invariant under a bilinear transformation. So, this we prove this we show that the cross ratio remains invariant under a Mobius transformation, which provides a way to represent a Mobius transformation that carries 3 distinct points Z1, Z2, Z3 to prescribed 3 image points W1, W2 and W3. So, this is the theorem. If W equal to Sz is a linear fractional transformation that maps the 3 distinct points Z1, Z2, Z3 onto the 3 distinct points W1, W2, W3 respectively, then Z minus Z1 over Z minus Z3 is equal to Z2 minus Z3 over Z2 minus Z1, Z minus W minus W1 over W minus W2, W2 minus W3 over W2 minus W1. You can see the cross ratio remains invariant from here, and this bilinear transformation also helps us in finding the required. This is the required bilinear transformation, which carries the 3 points Z1, Z2, Z3 to W1, W2, W3. You can see here when Z equal to Z1, this becomes 0 left side, and so W equal to W1. Okay, and when Z equal to Z3, okay, this becomes infinite, and so W becomes W3. And when Z equal to Z2, okay, then left side becomes 1, and here right side becomes 1 when W equal to W2. Okay. Now, let us, in order to prove this, let us say R be the linear fractional transformation Rz equal to Z minus Z1 over Z minus Z3, Z2 minus Z3 over Z2 minus Z1. Then we can see that first of all, this is the fractional transformation. Why? Because Rz equal to, it is not of this, it can be written in this form, Z2 minus Z3 into Z minus Z1 into Z2 minus Z3 divided by Z2 minus Z1 into Z minus Z3 times Z2 minus Z1. So, you can see it is of the form Az plus B divided by Cz plus D, but it will be called a linear fractional transformation provided we show that Ad minus Bc is non-zero. So, let us prove that here A is Z2 minus Z3, B is minus Z1 into Z2 minus Z3, C is Z2 minus Z1 into Z2 minus Z1, and D is minus Z3 into Z2 minus Z1. They satisfy the condition that Ad minus Bc is non-zero. So, Ad minus Bc is how much here? Z2 minus Z3 into D. D is minus Z3 into Z2 minus Z1. Okay. Then minus B is equal to minus Z1 into Z2 minus Z3 minus B C. Okay. So, C is Z2 minus Z1. Okay. Now, from here what do we notice? Z2 minus Z3 and Z2 minus Z1 we can take common. Okay. So, then taking these two factors common, Z2 minus Z3 into Z2 minus Z1, what we get? Minus Z3 here, and here what do we get? Z2 minus Z1, Z2 minus Z3. So, plus Z1. Okay. So, Ad minus Bc is Z2 minus Z3 into Z2 minus Z1 into Z1 minus Z3. Now, Z1, Z2, Z3 are your distinct points. So, Ad minus Bc is not equal to 0, and therefore, this transformation is a linear fractional transformation. Now, furthermore, you notice that Rz1 equal to 0, okay, Rz2 equal to 1, and Rz3. When Z goes to Z3, you see that Rz goes to infinity. Okay. So, Rz3 equal to infinity. Now, consider also this transformation, Tz equal to Z minus W1, Z minus W3, W2 minus W3, W2 minus W1. Then here again, when you replace Z by W1, Tw1 equal to 0, Tw2 equal to 1, Tw3 equal to infinity. Therefore, the points Z1, Z2, Z3 are mapped onto the points W1, W2, W3 respectively by the bilinear transformation T inverse Rz. How? Because T inverse Rzj, okay, R Z J, let us call them as Z1, Z2, Z3, R Z J are 1 0 infinity. Okay. So, R Z J goes to 1 0 infinity. T inverse maps and okay, and T inverse of T maps W1, W2, W3 to 0 1 infinity. Okay. So, T inverse maps 0 1 infinity into W1, W2, W3. So, R Z J goes to 0 1 infinity and 0 1 infinity under T inverse go to Wj. Okay. So, therefore, the points Z1, Z2, Z3 are mapped to points W1, W2, W3 respectively by the bilinear transformation T inverse Rz. T inverse Rz is a bilinear transformation because T is a bilinear transformation, its inverse is a bilinear transformation, and then T inverse and composition R is also a bilinear transformation. Now, consequently, it follows that 0 1 infinity are mapped onto 0 1 infinity respectively by this composition. So, let us look at this composition S inverse T inverse Rz. So, how we get this 0 1 infinity are mapped into 0 1 infinity. Okay, what happened was here S inverse T inverse Rz. Okay, S inverse T inverse Rz did what? From here let us look at this T inverse Rz. T inverse Rz carries Z1, Z2, Z3 to W1, W2, W3. Okay. So, T inverse Rz carries Z1, Z2, Z3 in Z2, W1, W2, W3. Okay, now we are applying S inverse on this mapping, S inverse on this mapping. Okay. So, let us look at this W equal to Sz, we are given this transformation W equal to Sz which maps Z1, Z2, Z3 onto W1, W2, W3. Okay. So, this means that Z equal to S inverse W. Okay. So, this means that W1, W2, W3 goes to Z1, Z2, Z3. Okay. Now, you see, let us take the points 0 1. We have seen that T inverse Rz carries Z1, Z2, Z3 to W1, W2, W3. Okay. Let us take the points Z1, Z2, Z3 to 0 1 infinity. Okay. Z1 equal to 0, Z2 equal to 1 and Z3 equal to infinity. Okay. Then Z1, Z0, 1 and infinity. Okay. Under this mapping T inverse Rz, okay, go to say W1, W2, W3. Okay. Suppose this goes to W1, this goes to W2 and this goes to W3. Okay. Under T inverse Rz. Okay. Under T inverse Rz. Then S inverse W equal to Z implies that these W1, W2, W3 go to Z1, Z2, Z3, that is 0 1 infinity. So, then S inverse W equal to Z. Okay. S inverse W equal to Z implies that W1, W2, W3 go to Z1, Z2, Z3. S inverse Wi go to Zi for I equal to 1, 2, 3. Okay. So, let us take 3 points 0 1 infinity in the Z plane. Okay. Then under T inverse Rz we have seen T inverse Rz maps the 3 points Z1, Z2, Z3 to W1, W2, W3. So, these 3 points 0 1 infinity, okay, 0 1 infinity they are supposing go to W1, W2, W3. Okay. Then and under the mapping T inverse Rz you see because of this Tw1 equal to 0, Tw2 equal to 1, Tw3 equal to infinity. Okay. So, T inverse 0 0 1 infinity, okay, 0 1 infinity under T inverse takes 0 1 infinity to W1, W2, W3. Okay. So, what we get here. So, T inverse S inverse W equal to Z implies S inverse W I equal to Z I. This means that the points 0, 1 and infinity are mapped into W1, W2, W3 and W1, W2, W3 under S inverse go to Z1, Z2, Z3. This means that and Z1, Z2, Z3 are 0, 1 infinity. So, 0, 1 infinity are mapped into 0, 1 infinity, and therefore, because of the theorem on fixed points, okay, the transformation must be an identity, because it fixes three distinct points 0, 1 and infinity. So, this S inverse T inverse R Z fixes three distinct points 0, 1 and infinity. So, it must be an identity map, and therefore, S inverse T inverse R Z must be equal to Z, and therefore, R Z equal to T of S Z. Okay. R Z equal to T of S Z, but S Z equal to W. So, R Z must be equal to T W. Okay. And R Z equal to Z minus Z1 over Z minus Z3, Z2 minus Z3 over Z2 minus Z1. T W is equal to T W equal to W minus W1 over W minus W3 into W2 minus W3 over W2 minus W1. So, we get this R T W. Okay. So, R Z equal to T W, and this gives us this transformation. Now, let us take an example on this. Construct a fractional linear fractional transformation that maps the points 1 I and minus 1 on the unit circle onto the points minus 1 0 1 on the real axis. So, we have W equal to A Z plus B over C Z plus D. Okay. This is bilinear transformation, and the transformation that maps 3 points distinct points onto 3 distinct points in the Z, from Z plane to W plane. We have Z minus Z1 divided by Z minus Z3 into Z2 minus Z3 divided by Z2 minus Z1 equal to W minus W1 over W minus W3 into W2 minus W3 divided by W2 minus W1. So, here we can put the value, this Z1 is 1, Z1 is 1, Z2 is I and Z3 is minus 1. Okay. So, Z minus Z1, so Z minus 1 divided by Z minus Z3, that means Z plus 1, and Z2 minus Z3, so I plus 1 divided by Z2 minus Z1, so I minus 1. This is equal to W minus W1, W1 is equal to minus 1 and W2 equal to 0, W3 equal to 1. So, W minus W1 means W plus 1, okay, and then W minus W3 is W minus 1, and W2 minus W3, W2 minus W3 is minus 1 divided by W2 minus W1 is equal to plus 1. Okay. So, what we get? Z minus 1 over Z plus 1. Okay. This I can simplify, I plus 1 over I minus 1, I can multiply by I plus 1. So, I plus 1 whole square divided by I square minus 1 we have, this equal to W plus 1 divided by W minus 1, and what we get into minus 1. W2 minus W3 is minus 1, W2 minus W1 is plus 1. Okay. So, this is Z minus 1 divided by Z plus 1, and here we have I square plus 1 which is 0 because I square is minus 1. So, we get 2I divided by minus 2, and this is W plus 1 divided by W minus 1 into minus 1. Okay. So, minus this means that W plus 1 divided by W minus 1 equal to, now this cancels with this, minus I and minus 1 here. So, this gives you I times Z minus 1 divided by Z plus 1. Okay. And when we simplify this, okay, we get W equal to, this gives you W equal to Z minus I divided by I Z minus 1. Okay. So, this transformation can be obtained by simplifying this equation. Now, let us find the, so this is the required transformation which maps 1 I minus 1 to minus 1 0 1, and we have to find the image of this interior of the circle mod z equal to 1 here under this transformation. So, let us take the test point z equal to 0, z equal to 0 goes to w equal to minus I divided by minus 1, this means I. Okay. So, I lies here, okay. I lies here. Okay. Now, 1 I minus 1, they are the points on the circle mod z equal to 1, you see 1 is here, I is here and minus 1 is here. We have taken 3 points on the circle mod z equal to 1 and we are looking for, and this these 3 points are being mapped onto minus 1 0 1 on the real axis. Okay. So, the boundary of the circle is going into the real axis of the w plane, okay. And we are now looking for the interior of mod z equal to 1, where does it go. So, we have taken a test point here z equal to 0 and we found the image of z equal to 0 under the bilinear transformation w equal to z minus I over I z minus 1 as I, and we see that I lies in the upper half of the w plane. So, this means that upper half of the w plane is the image of mod z less than 1. Okay. Upper half of the w plane means b greater than 0. So, mod z less than 1 goes to mapped into b less greater than 0. Okay. Rather we could write mod z less than 1 is mapped into onto b greater than 0. Okay, let us take one more question. Construct Mobius transformation that maps the point minus 1 1 minus I 1 and infinity on the line y equal to x minus 1. You can draw the line y equal to x minus 1. So, this is your x equal to 1 and when this is when x is 0, it is minus 1. So, this is the line y equal to x minus 1 in the z plane, and we have construct the Mobius transformation that maps the point minus I minus this is minus pi. Okay. This point is minus I, this point is 1 and we have a point infinity on the line. Okay. So, they are mapped onto the points 1 I and minus 1. 1 I and minus 1 on the unit circle, that means under the transformation straight line is going into circle. This is mod z equal to 1. The points are 1 I and minus 1. Okay. Let us find the transformation. So, we have z minus z 1 over z minus z 3, z 2 minus z 3 over z 2 minus z 1. Okay. This cross ratio, okay, we have this equation w minus w 1, w minus w 3, w 2 minus w 3, w 2 minus w 1. Okay. The cross ratio for the points minus I 1 and infinity, okay, will be this following. For z 1 equal to minus I, z 2 equal to 1, z 3 equal to infinity, okay, will be limit z 3 tends to infinity, z 2 minus z 3 divided by z minus z 3 into z minus z 1 over z minus z 3 or z minus z 2 minus z 1. Okay. So, we can write it as limit, this limit we can find by taking z 3 goes to 0 and z 3 by 1 by z 3. So, z 2 minus 1 by z 3 divided by z minus 1 by z 3. So, this will be limit z 3 goes to 0, okay, z 2 z 3 minus 1 divided by z z 3 minus 1. So, this is 1. Okay. So, this will be replaced by 1, okay, and we are this gets reduced to z minus z 1 divided by z 2 minus z 1. So, we have this equation becomes z minus z 1 divided by z 2 minus z 1 equal to w minus w 1 divided by w minus w 3 into w 2 minus w 3 divided by w 2 minus w 1. So, now let us put the values here. Z 1 is minus I. So, z plus I, okay, over at z 2 minus z 1. So, 1 plus I equal to w minus w 1. So, w minus 1 divided by w minus w 3. So, w plus 1 and then w 2 minus w 3. So, I plus 1 and then w 2 minus w 1. So, I minus 1. Okay. So, this is the equation. This can be simplified and we get w equal to this gives you w equal to, after simplification, z plus 1 divided by minus z plus 1 minus 2 I. So, this is the required transformation which maps the points minus I, 1 and infinity to 1 I and minus 1 on the unit circle. So, with this I would like to end my lecture. Thank you very much for your attention.